revision video of digital electronics, and this is a special video which I'm doing for the preparation of HSLC Technical Assistant, and also it is useful for all the other PSC examination and also all competitive examinations of electrical, electronics and all other related branches to electronics. Okay, so there's a lot of branches in which you study digital electronics. So for all these branches, this digital electronics formula revision video will be very much useful. And I'm sure that if you watch this video till the end, you can at least answer 3 or 4 questions in your competitive examination. Okay, so this digital electronics is given a lot of weightage when comparing to the other subjects. If you see the competitive examination, you can find a lot of questions from these areas of number systems, digital electronic circuits, gates, Boolean simplification, also ADC. All these areas are very important. Okay, so I'll try to include as much as possible in this video, and we'll be doing a part 2 for the next set of formulas and equations. Okay, so starting off with the basic things of digital electronics, we know that logic gates are very important when compared to the other topics and also the other areas. So why these gates are important? Because either they'll be asking questions related to single gate, or they'll be clubbing all these gates and forming a circuit, and you have to find the end result of this circuit. Okay, so anyway, you need to find, or you need to know what is the equation for the gate, how the gates look, how the truth table is. Everything is very important. So moving on to the basic gates: AND gate, OR gate and NOT gate. First thing is that you should be able to identify the gate. AND gate is looking like this. Okay, this is an AND gate, and the equation for the AND gate is y is equal to AB. It is a product. It is a multiplication gate, AND gate. And whenever both the values is 1, we know that 1 into 1 is only 1. 1 into 0 is not 1. It is always 0, and 0 into 0 is also 0. Similarly, when A and B is taken as the input, output will be 1 only when both the inputs are 1. That is the truth table of a AND gate. So my request is that if you are interested in watching this video till then, please make a note of this video. It will be very useful to you, trust me. Okay, so A and B, whenever A and B both are 1, your output is 1. OR gate. OR gate means taking the sum of both. So we know when 1 plus 0 is also 1 and 1 plus 1 is also 1. I'm talking about the digital thing. Okay, so generally 1 plus 1 is not 1. So, but in digital, that is in binary addition, 1 plus 1 is 1. So if you talk about the truth table, so this is the gate structure. Okay, so this is the structure of a OR gate. A and B are the inputs, y is equal to A plus B is the output. Truth table is whenever any of these A or B is equal to 1, your output is 1. But when both the inputs are 0, your output is 0. So 0, 0 is 0, 0, 1 is 1, 1, 0 is 1, 1, 1 is again 1. Okay. Now moving on to the next gate. So these are the 3 gates which we study as basic gates: AND, OR and NOT gates. From these gates, the next other gates are generally derived or produced, we can say. NOT gate means it is taking the complement. That is, if you are giving a 1, it will produce a 0. If you are giving a 0, it will produce a 1. That is a complementing gate. It is called a NOT gate. So if A is the input, what will be the output? It is A bar. Okay, so if 1 is given, 0 is output. If 0 is given, 1 is output. That is the truth table. Moving on to the next gates, which is NAND gate and NOR gate. Now, another important question which I have seen in these competitive examination question papers is that which is the logic gates which is called as universal logic gates. The answer is NAND gate and NOR gate. Now, why this is called a universal logic gate? Because we can derive all the gates, that is all these gates, we can derive with the help of this NAND gate and NOR gate. So, since it can be used to derive any gates from it, it is called a universal gate. Okay, I hope the concept is clear. So, you should be able to answer that the universal gates are NAND and NOR gates. Okay, so moving on to the symbol and the equation and the truth table. The AND gate plus a bubble in front is called a NAND gate. Now this bubble in general also or in gates also indicates nothing but a NOT gate, this one. That is, if you put a bubble in front of the expression, it is getting complemented. Okay. So if A and B are the input, Y will be AB bar. That is the complement of your AND gate. That is called NAND gate. So you can also say this NAND as NOT plus AND. Okay. I hope it is clear. Moving on to the truth table. If A and B are the inputs, Y is the output, and Y will be whenever that is whenever any of this that is values is 0, you have to get a 1 because it is AB bar. So 0 0 output is 1, 0 1 output is 1, 1 0 output is 1, 1 1 output is 0. If you see the truth tables of AND and NAND, it is just the opposite. So wherever it is having ones in AND gate, there it is 0. Wherever it is having zeros, there will be 1 in case of this NAND gate. Okay, similarly for the next gate, which is NOR gate, it is a complemented gate of OR gate. So, I'm sorry, there is a 0 or a bubble in front. I have forgot to put it. Sorry. So, AB complement indicating a bubble. So, Y is equal to A plus B complement is the NOR gate. So, what will be the truth table? If A and B are the inputs, Y is the output. Then, whenever any of these values is 1, output has to be 0. Or if you find it difficult to study, it is nothing difficult to study. But anyway, if you have some problem, this OR gate's truth table just complemented is the truth table of NOR gate. That is for 0 0 is 1. 0 1 is 0, 1 0 is 0, 1 1 is again 0. So whenever one of the input is 1, output will be 0. Okay. So that is a case for a NOR gate. I hope it is clear. So please note this down. Okay. Please make a brief noting of these formulas. It is very useful for you because if you are trying to get into government sectors or any sectors, private sector or any companies, if you make a formula revision notebook, which is very useful. Okay. Next, moving on to the other gates, which we are commonly seen in nowadays in all question papers, is XOR gate. XOR gate, if it is looking like this. Okay, so if A and B are the inputs, output will be Y is equal to A B bar plus A bar B. Now, the symbol of XOR, I am writing it here. A, in the circle, there is a plus sign. So, this is XOR. Because in question paper, sometimes you can only find this symbol. It indicates nothing but XOR. XOR means inside a circle, there is a plus sign. So, what is the equation? That is, what is the output equation? It is A B bar plus A bar B is the output equation. Moving on to the truth table. See, if you see this expression for output, 1, 0 plus 0, 1. You can give it like that. If A and B are given as 1, 1. It will be A B bar plus A bar B. So, 1 0 plus 0 1. So, whenever this combination is coming, 1 0 and 0 1 is coming, output is 1. For all the other cases, output is 0. Similarly, for A, B as input, Y as output, truth table is 0 0 is 0, 0 1 is 1, 1 0 is also 1 and 1 1 output is 0. That is whenever the combination of inputs are same, output is 0. When it is different, that is one input is 0, other input is 1 or vice versa, your output has to be 1. Okay, so that is the case for a XOR gate. Moving on to the XNOR gate, and the symbol is A. Inside the circle there is a dot. It is indicating XNOR. Okay. So, in XNOR, if A and B are the inputs, your output expression or Y is equal to AB plus A bar B bar. That is, your inputs has to be same to produce an output 1. That is, it can be either 1 1 or it can be either 0 0. So, what will be the truth table? For 0 0 combination and also 1 1 combination, your output is 1 and your output is 0 for all the other cases. Okay. So, 0 0 is 1, 1 1 is 0. For 1 0 and 0 1, output is 0. Very simple is this. You can relate these gates because you know that NAND and NOR are derived from this OR and AND. So you can study it in a combined way. And also, if you prepare, I'm telling it once again, please prepare a notes of this gates. It is very useful. You only require one page. Draw small figures and small truth tables. It will look good also. It will be easy to refer also. Don't use a lot of papers and draw big structures. Small symbols and small truth tables, and make it cute and make it easy to study. So please make a note of this. It is useful for you for all examinations of electronics. Okay. Moving on to the next area of digital electronics, which is Boolean simplification. Okay. So I also want to tell you that I have done a detailed video on number systems, various number system conversions, and also flip-flop summary or flip-flop equation revision video I have done. And also I have done a detailed video on K-maps. There are 2 videos on K-maps. Okay, so I'll link all those videos. There are 4 important videos for you along with this video in the description box. Okay, please do refer that videos also. So I'm not doing a number system revision in this video because I've already run a video. Okay, and also I'm not doing the flip-flop areas. So moving on to the Boolean expressions. So in the Boolean expressions, I'm not stuffing all the unwanted equations or unwanted things because it is very difficult for you to study at the end time preparation. Because if I'm going to teach you something very new, it is not called a formula revision video. It's called teaching. So I'm going to only give all the important things you need. Boolean expressions, the important Boolean simplification things you need is this much. A plus A. This A can be any variable. It can be B plus B, it can be C plus C, it can be 1 plus 1 or 0 plus 0. You can put A in various forms. In digital, okay, in binary. So A plus A is A, and also A into A is A. That is, if you multiply A into A into A into A into A, it is A. This law is called idempotent law. Okay, because sometimes they can also ask what is idempotent law from this expression. So that's why I have written this term there. And another important thing while simplifying Boolean expressions you need is A plus, consider that there are n number of variables, plus 1. The result will be equal to 1. Okay. And also another 2 things you require for Boolean simplification is A plus A complement. That is 1 plus 0. If you are taking, you can not take in that way. Anyway, if A plus A complement is taken, this A can be again any variable, B or C or any variable, plus its complement. While simplifying Boolean expressions, I'm telling you, that is A plus A complement. That is any variable plus its complement is equal to 1. And if you take the product of A and 0, that is A into 0 is equal to 0. This is called identity law. Okay. And also you should know this thing, that A into A complement. A into A complement. What is that? It is 0. Okay. So you should also know this. Please note these expressions because these expressions will be very useful if you do Boolean simplifications. This is also important. Okay. A into A complement is 0. That is, if you take the product of a variable and its complement, it's 0. But if you take the sum of a variable and its complement, it is equal to 1. I hope you have noted. Next, moving on to the most important equation or Boolean expression, it is De Morgan's law. De Morgan's law states that this is very useful. Okay. A plus B, the whole complement, can be written as A complement into B complement. And AB, the whole complement, can be written as A complement plus B complement. Here again, the variables can vary. Can be A or B, B or C, C or D or any variable, but you can write it in this form. That is, if you face an expression like AB, the whole complement, you can write it in the form of A complement plus, A complement plus B complement. Okay, so this is called De Morgan's law. Please note this down. Now we are going to see some of the other commutative law and associative law, only the important expressions. Okay, the expressions which I have generally seen in exam papers. So for commutative law, commutative means if it is given in the form A plus B, you can write it in the form B plus A. You can reverse the order. Okay, so if a plus b is given, you can write it as b plus a, and also if a into b is given, you can write it as b into a, and a XOR b can be written as b XOR a. Then a into b the whole complement or ab complement can be written as b complement into a also. So these are some commutative laws. Now moving on to the associative laws, this is also very important while simplifying the Boolean expressions. If the expression is a plus b into c in brackets, then you can write it as a plus b, that is you can associate the variables a plus b plus c. You can associate a and b now. Then similarly for a XOR b XOR c, you can write it as a XOR b XOR c. And also product also a into b into c, you can write it as a into b into c. And for XNOR also a XNOR b XNOR c can be written as a XNOR b XNOR c. So this is very important because I have seen some questions with associative property. You can do it in a very faster way. Okay. Now moving on to the another things which this sum of product and product of sum I have explained in detail in my K-map video. So please see that video. Okay. Now before that, dual form, that is if the question is to take the dual, means you have to change all the sum signs, you have to change as products, and vice versa also. If it is product, you have to change as sum. And if 1 has been given, for if you take the dual of 1, it is 0, or in the opposite form. Okay. Moving on to the sum of product and product of sum. What is called sum of product? If you write in this form, that is f is equal to a into b into c plus a bar b bar c bar plus like that. If you are writing the sums of product terms, it is called sum of products. Okay. And in sum of products, we generally look for min terms, and it is 1. And if it is in the product of sum POS form, we represent POS using pi letter. Here we use sigma. Sigma is SOP. Product of sum or POS is pi. And if product of sum, we write it as a plus b plus c. It is a sum term. See, it is a sum term. And then we are taking the product with another sum term. And in product of sum or POS, we write max terms. And I'm writing it, that is I'm saying it for the K-map simplification also. In K-map simplification, it is POS form. That is if it is pi, it is, we are going to write zeros in that columns. Okay. And we look for max terms in POS, and it is max terms, we call them as 0, or zeros are max terms. Okay, I hope it is clear. SOP is written using sigma, POS is represented using pi. Okay. The next session that we are going to discuss is the session of mux, demux, encoder and decoder. So how is this mux, demux and everything, and what is the number of input, output, what are the number of select lines, all these things we are going to see. Okay, so if you are talking about mux, mux means multiplexer. So multiplexer, what it is doing is, it is generally going to combine the we generally call it as multiplexing. Okay, so or you can say according to the particular select line, it is going to produce an output. Okay, so if S is a select line and I0 and I1 are the inputs, your output will be S bar I0 plus S I1. That is, if your select line is 0, means it is going to select I0. Then if your select line is 1, it is going to select I1. This is a very simple or a very basic 2:1 multiplexer. Now moving on to the 4:1 multiplexer. 4:1 means there are 4 input lines and only there is a single output. Okay. So that is a basic thing for a 4:1 multiplexer. 4:1, there are 4 inputs, and based on the select lines, there are 2 select lines for a 4:1 multiplexer. There is a 1 output. And based on the various combinations 0, 0, 0, 1, 1, 0 and 1, 1, I0, I1, I2 and I3 will be selected. These are very basic things. Now, if you talk about the general thing for a multiplexer, if there is n number of select lines, then you can have up to 2n number of inputs. For example, if n is 1, means 2:1, means 2:1 is 2. That is 2:1. So this is how you can generally represent a multiplexer. and there is only one output for a multiplexer. Okay, so that is called multiplexing. Based on the select lines, you are going to select these signals and provide it to the output. Okay, so how can you generally write a multiplexer is, it is having 2 raised to n inputs and 1 output. That is 2 raised to n is to 1. Where with how many number of select lines? N number of select lines in the bracket. So that is how you can represent a multiplexer. Or you can write in this form n number of select lines if there is n number of select lines, or 2 raised to n inputs. Or in reverse order you can say, if there are 2 raised to n number of inputs, then there should be n select lines and output is anyway only 1. Now moving on to the, so this is a 8:1 multiplexer. So it is having 8 inputs, 3 select lines and 1 output. So you should be able to figure out these things, because in sometimes the question can be from the figure, identify the circuit. So these type of questions I have also seen. So that's why I have written these things. If it is having select lines, it can be multiplexer, and also this combination is there, 2 raised to n inputs, n number of select lines. Likewise, okay. So that is the case for a multiplexer. Now if there is 8 input means 3 select lines and 1 output. Okay, that we have discussed. Moving on to the next thing, which is demultiplexer. Demultiplexing means, so in multiplexing we are going to add or multiplex the signals. That is, from the combination we are going to select one. Whereas in demultiplexing we are going to pass on this one signal through various channels. Likewise. Okay. So demux is having a one input. There are okay, we'll talk about the select lines first. There are 2 select lines. This is a 1:4 demultiplexer. So there are 2 select lines and 2 raised to n number. If there is, the n is 2. See, there are 2 select lines, means n is 2. So 2 raised to n number of outputs can be there, and there is only one input. And this input we are going to pass on through any of these channels or any of these output lines. Okay, so this is a 1:4 demultiplexer. So there are 2 select lines, 4 outputs, 1 input. That is 1 input, 2 raised to, generally if you are talking 2 raised to n number of outputs are there. There is n select lines. Okay, so this select lines, if you see select lines, that can be multiplexer or demultiplexer. So multiplexers has number of inputs more, output is 1. Demultiplexer has number of outputs more, input is 1. That is the basic things. You should have a, on a competitive exam point of view, you should have these things or these ideas in your mind. Moving on to the next section, which is encoder and decoder. So encoder, what is encoders? They are generally used for producing codes. Okay, that is called encoder. Whereas decoder means from the code, it is going to figure out what is the actual value. So in a very basic way, if you can talk about this encoder and decoder, you can talk like this. Okay. So let us see what is a encoder and a decoder. An encoder is going to produce a code. Okay, so based on the inputs in any of these lines, for example, if there is an input in the line A2, there are various lines. It is a 8:3 encoder. That is, 8 inputs are there. There is a 3 outputs. That is called 8:3 encoder. Okay, so generally encoder means it is producing a code word. Code word means a small word. So the number of output lines will be smaller in case of encoder. Whereas in the case of decoders, it will be the reverse. I'm just giving a trick to identify whether it is encoder or decoder. Okay, so consider that this is an encoder. There are 8 input lines. There is 3 output lines or a code of 3 bit size. Okay, so consider that there is a 1 in this line called A2. Okay, so you need to produce a code word for this particular combination with a 1 in A2. All the rest of the lines are 0. So you need to produce a what? A code corresponding to a 1 in line A2. That in input line A2 is having a 1. So you have to produce a code for that. Okay, so how would you produce it? It is like, we know that in binary, if you can represent A2 is 3 bits, it will be, that is 2. If you are representing in 3 bits, it will be 0, 1, 0, right? This is the code corresponding to 2. So A2 generally indicates 2. Okay, so binary 2, or if you want to produce a code like that, your Q1, Q2 and Q3 will be 0, 1 and 0. Similarly, if you want to have a, I'm just giving you a rough example, okay. If you want to have a 1 in A3 and consider all the other lines are, all the other input lines are 0, means the code word generated will be 0, 1, 1. So likewise, an encoder will generate code. So there are various types of encoders. So a basic encoder will be doing this, okay. And consider there is a 1 in, for example, A4. It will be 100. The code generated is 100 in Q1, Q2 and Q3. That is Q1, Q2 and Q3 will be 100. So this is how encoders work. Okay, so this is the basic working of encoders. And talking about the number of inputs, number of outputs and all, there will be 2 raised to n number of inputs and n number of outputs. For example, if n is 3, means 2 raised to 3 is to 3. Or if n is 2, 2 raised to 2 is to 2. This is the case for a encoder. For a 2 raised to 2 number of input lines, it will have a code of length 2 bits or 2 codes, or you can say 2 output lines. In input and output way, you can say it like that. Okay, 2 raised to n is the case for a encoder. Okay, there are 2 raised to n input lines, n output lines. Okay, now moving on to the decoder session, it is going to decode everything. Okay, so you are going to give a single code. It will produce a, that is it will decode it. So if it is a 1:2 decoder, based on the values on A, you are going to get outputs on Q0 and Q1. Consider if A is 0, then you are going to get a value in Q0. If A is 1, you are going to get a value in Q1. This is the basic working. Similarly, there is 2:4 decoder and 3:8 decoder. So just the reverse of encoder is decoder. Okay. Similarly, in coding also, communication also, we know that encoding's opposite is decoding. Okay. So here, how many number of inputs and how many number of outputs? Let's talk about that. If there are n number of inputs, there will be how many number of outputs? There will be 2 raised to n output lines or outputs. Okay. So this is a case for a decoder, and encoders and decoders doesn't have any select lines. This is another trick to identify the circuit, whether it is a mux, demux or an encoder or a decoder. Encoders and decoders doesn't have select lines, whereas mux and demux is having select lines. Okay, so this is some tricks I'm giving you to identify from the figure whether it is an encoder, whether it is how many number of, that is how many number of inputs are there in that encoder, how many output lines can be there. All these things you should be knowing. So these are the general things about mux, demux, encoder and decoder. Next we are going to talk about another important session, which is half adder, full adder, half subtractor and full subtractor. Okay. So this equations itself is very important because there are question papers in which I have seen the equations. What is the sum equation? What is the carry equation? Like this questions can come. Okay. So please note this down. We are going to talk about first half adder. I have not drawn the truth tables for full adders because if you know half adder, it is going to be like that. You can also draw 3-bit calculations of full adders and full subtractors. Okay. So half adder, if you are going to give A and B, there will be 2 inputs, A and B. There is no carry input for the case of a half adder, and you are going to get sum and carry. Okay. So if 0, 0 is being given to the sum, if 0, 0 is being given, sum is 0, carry is 0. If 0 and 0 is added, there is no sum, there is no carry. If 0 and 1 are added, sum is 1, but there is no carry. Now 1 and 0 added, again sum is 1, carry is 0. But if you are going to add 1 and 1, sum is 0, carry is 1. Very, very important thing is the truth table. Okay. Now from this, you are going to get a sum, that is when you are going to get your sum is 1. From this truth table, what is the sum? Sum is 1 whenever 0, 1 or 1, 0 combination is obtained. Okay, so it is nothing but XOR. So you can write sum as A XOR B, carry is, this is a table for a AND gate. So it is a AB. A into B is carry. Okay, so you can write sum as A XOR B, carry as A into B. And also you can draw the circuitry like this. If you are able to study this, you don't need to study this or anything, just draw this and you will be able to, that is, just have this thing in mind. Sum is A XOR B, carry is A into B. Moving on to the half subtractor. Half subtractor, okay, so half subtractor means it is going to take the difference of two numbers. There is no carry or anything. Only two numbers is being given to it, A and B. The difference is taking the difference of these A and B. So for A and B are 0, difference is 0, borrow is 0. We say borrow, not carry, in terms of subtractor. So again, if A is 0, B is 1, difference is 0 minus 1, difference is 1, borrow is 1. Okay. Then if A is 1, B is 0 means 1 minus 0. So difference is 1, borrow is 0. There is no borrow if you, that is, if you subtract 0, that is, if you do this operation 0 minus 1, then your difference is 1 and borrow is again 1. Okay. And if you are going to do 1 minus 0, 1 minus 0 means difference is 1, borrow is, there is no borrow if you subtract 0 from 1. But if you do this 0 minus 1 means 0, that is from 0 you are going to subtract 1. So the difference is 1 and borrow is again 1. So this is the thing you have to keep in mind. Okay. Now that is one thing. Then 1 minus 1. If 1 and 1 are being given as A and B, then difference is 0. 1 minus 1 is 0. Borrow is also 0. Now if you write this in terms of equations, difference you can write it as A XOR B again, because you know that here for the 0, 1 and 1, 0 combination, again the difference is the value of difference is 1. So you can write it as A XOR B. But the case for borrow, you have to consider whether you are going to subtract A from B or B from A. So if for A minus B, the borrow is A bar B, and for B minus A, it varies, right? For the case of difference, it varies whether you are going to subtract A from B or B from A. So that's why the borrow is written in two different equations. A minus B for A bar B for A minus B, and A B bar for B minus A. That is, from which number you are going to subtract, it depends on the borrow. Okay, I hope it is clear. Moving on to the equations of full adder and full subtractor. Directly I have written to some equations because this is also very important. Okay, sum is, for a full adder, sum is A XOR B XOR C. We know that in case of full subtractor, you are going to give two inputs A, B, and also with that you are going to give carry. So sum is, expression for sum produced by full adder is A XOR B XOR C. Carry in, that is C. Okay, carry out expression is, you can write it in two forms. You can write it as AB plus BC in plus AC in. This is also important, and you can also write it as AB plus A XOR B into C, because both these expressions can come in questions. So please note down these two expressions. Moving on to the full subtractor equations. Difference for a full subtractor will be A XOR B XOR C. Similarly, the case for half and full subtractor, half adder and half adder and half subtractor, we know that the difference equation and the sum equations are same, right? Similarly, for full adder and full subtractor also, sum equation and carry equation, sum equation and difference equation are same. For the case of full adder, sum is A XOR B XOR C. And also for the case of full subtractor, difference is same as that of full adder's sum. That is A XOR B XOR C is a difference equation for a full subtractor. I am giving you a trick to study. Okay. So if you want to study the equations for full adder and full subtractor, for the case of full adder, sum is A XOR B XOR C in, and for the case of full subtractor, the difference is A XOR B XOR C in. Both are same. Now moving on to the borrow out for a full subtractor. is A bar B plus A XOR B bar C. This is the this is the Borrow equation for a full subtractor. Now just see this equation. Here the carry out for a full adder is AB plus A XOR B into C. And have a look on this equation and this equation. Only difference is that here there is a complement on A for the borrow out, and here there is a complement on this A XOR B for the borrow out. So you can study these equations in a connected manner. You don't have to mug up. If you know one equation, there is some variations for the equation for a full subtractor. If you know the equation for full adder, means you know by equations it is very easy to connect and study. Automatically you will be knowing this equation for full subtractor also. So I hope these things are clear to you now. Now moving on to the equations for ADC, and also we'll see the main equations and concepts of Mealy and Moore machines, the state machines, finite state machines also. Okay, equations for ADC, the main equation is ADC resolution. Okay, so if the ADC full scale voltage is given, then ADC resolution is equal to V full scale by 2 raised to m, where m is the number of bits of the ADC. Okay, but if the maximum and minimum voltages of the ADC is being given, then Vmax minus V minimum by 2 raised to m. Now this Vmax minus V minimum is nothing but V full scale or full scale voltage of the ADC. Okay, so V full scale by 2 raised to m, where m is the number of ADC bits. So this is one important equation which is useful for doing problems also, and also theory also. Now signal to quantization noise ratio. We know that in case of ADC there are 2 steps. First step is sampling of the signal, analog signal, then quantizing of the analog signal. And at the end of this sampling and quantizing, you will get your digital representation, right? So that is a principle of ADC. I have also done a separate video on the principle of ADC or analog to digital conversion. Please have a look on that video. I'll share the link in the description box. Okay. So signal to quantization noise ratio is given by 20 log 10 2 raised to q, where q is the number of quantization levels. Okay. So that is the equation for signal to quantization noise ratio. Another important equation while considering the sampling of the signal is the signal has to be sampled at Nyquist criteria. We know that this is a very useful equation, because I'm telling you, because I have not seen any question paper without at least one Nyquist criteria question. This is very useful. Okay, so this is the relation. Sampling rate or Fs should be greater than or equal to twice the maximum frequency of your signal. Okay, so this is called Nyquist sampling rate. Only if the signal has been sampled at this rate, your signal can be reconstructed perfectly. Otherwise, while reconstructing the signal back to the analog version, it will have some missed out portion. Okay, so it won't look like your original signal. Now another important thing which I have seen in the question papers is regarding the number of comparators required for ADCs. In the case of flash ADCs and normal ADCs, the number of comparators required is 2 raised to n minus 1, where n is the number of bits of a ADC. So if n is the number of bits, then it requires 2 raised to n minus 1 number of comparators. But if this is the case for a folding type of ADC or a folding flash ADC, if the ADC is a folding type, then the number of comparators can be actually reduced to 2 raised to n by m, where m is the number of foldings. Okay, so this purpose of folding ADC is actually to reduce the number of comparators. 2 raised to n by m, where m is the number of folds. So these are the most important equations regarding to the ADC. Okay, now if you are looking for DAC, then DAC generally the accuracy problems and all those problems of DAC area is coming. So DAC area or DAC, the resolution is 2 raised to n, where n is the number of bits of a DAC. Okay, so these are some important equations which I feel that you should use or you should study or will be useful for you if you're preparing for these technical assistant examination, because I've seen questions coming from this area. That's why I've included all these equations. Okay, Now moving on to the equations of melee state machine and Moore state machine. So FSMs can be generally classified as melee FSM and Moore FSM. Now what is the difference between this melee FSM and Moore FSM? I'll draw it in the form of state diagrams and explain. Okay. So I'm going to draw a very rough figure. I'm going to draw a melee FSM now. There are various states A, B, C. Okay. There are three states A, B, C. Consider there are three states. You can represent a melee FSM as input bar output. This is the representation in each branches. And here also input bar output. Here also input bar output. So this is how a melee FSM is generally going to look like. That means in each branches you are going to draw input bar output, means each output. See, here output is there is output, here also there is an output. So this output is depending on the states also and also depending on the input also. Okay, so here the output will depend on states, comma, inputs. So the outputs depends on both these things. Then it is called a, or that type of representation is called a melee FSM. Okay, so that is one thing you should know about the melee FSM. Its output depends on state also and also various inputs at each state. Okay, whereas in case of a Moore FSM, I'm going to draw the state diagram first. Okay, you are going to draw it like this. Here again there are three states. C bar 1. Okay, there is input here, there is input. This input can be either 0 or 1. Okay, so in case of a Moore FSM, if you see the states inside the state circle, you can see A bar 0 means A bar, the output of that state is 0. B bar 0 means output of that B state is 0. C bar 1 means output of the C state is 1. So that is crystal clear, or that makes it crystal clear that the output is nothing dependent on the input, but it is only depending on the states. Each state is having a specific output. So it has nothing to do with the input. Only output is a function of state variables. Okay. So you can write output depends on only states, not on the inputs. And in the branches or in these arrows, if you see, you are only writing the inputs, not input bar output. Okay. So this is the difference between melee and Moore FSM. So why this I'm explaining is sometimes it can come as questions like in case of a Moore FSM, output depends on dash and dash. Okay, so these are important. So I hope this concept is also clear to you now. So these are some concepts and some equations which I have included in this video. I'm telling it once again, I've told in the beginning of the video also. I have done a separate video for number systems, flip-flop summary, also K-map, and also for ADC, analog to digital conversion, basic things, sampling and everything I have explained in a separate video. So I'll link all those videos in the description. Please have a look on that videos one by one. So by covering all these videos, I'm sure that you will be pretty covered with the digital electronics session. I'm not talking the entire theory, I'm talking in an exam point of view. Okay. So these are some preparation videos which I'm planning or I'm doing for mainly the ISRO technical assistant examination. And also I'm receiving a lot of requests to concentrate more on the HSFC examination, which is going to happen very soon. I'll be doing a lot of question answer sessions, question paper solutions. I'll be doing that. Okay, so I hope that this video was useful for your preparation. If yes, please do give it a thumbs up. It is always an encouragement for me to do more videos. If you are liking the video, please give it a thumbs up. And also share these videos with maximum of friends. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.